Hello, welcome everyone. So in the previous class we discussed about the single-ended signal and the differential signal. So what are the advantages and disadvantages of single-ended and differential signal? In the differential signals we need two input. So for an amplifiers we can use common source amplifiers. We have common drain, common gate and common source among these three. So we have common source is the better compared to the common drain and common gate, as it has a good input and output impedance. So and then for differential input we use the another input to be as the source terminal for the common source amplifier to give a differential input, but we cannot give input directly to the common source because the input impedance will be very less. So because of loading effect the input, we will not be able to get a gain due to the input from the source terminal. So we give the input from to the source terminal through buffer, so that loading effect is neglected here and it becomes equally the same. You have two transistor M1 and M2. So this M2 is nothing but the buffer, where we give the input for the buffer is to the gate terminal of transistor M2. So the input impedance of both the signal input 1 and input 2 will see the same impedance, and we will get the output from the drain of both the terminal. So this is the differential output what you get, which is VO1 with respect to VO2. So the differential output is 2 times GM onto R of V in, if the input is V in 1 and V in 2, right? So this is the differential amplifier what we have discussed. So coming to the next topic, the study of the differential amplifier in common mode operation. Okay, common mode operation. So in the today's class we will discuss about the study of this differential amplifier circuit what we have discussed earlier, that is the differential amplifier with the resistive load, right? And this is the current source, this is V in 1, this is V in 2, both are NMOS transistor, and the resistor with the common supply VT, and this is VO1 and this is VO2. So this is the circuit what we have. So now during common mode operation, common mode means the input is common for both the terminals. This is basically a DC analysis, right? So DC analysis, because this circuit to act as an amplifier, the first thing we need to provide a DC biasing, right? So first thing we have to provide a DC biasing, and the second thing is to ensure that the transistor are in saturation region. So circuit to work as an amplifier, these two are the important points has to be taken care, that the DC biasing has to be provided and ensures that the transistor should be working in the saturation region, right? So here we have two transistor M1 and M2, and we implement this current source using the transistor again, right? So this I will redraw it. So this tail current I can implement it using MOS transistor by giving an external bias. This is M1, M2 and M3. This is V in 1 and V in 2, right? So now for the common mode operation, what we do here is we will short both the inputs, that is V in 1 and V in 2. Both the inputs are shorted and we name it as VI CM, that means input common mode, right? So this is the common mode operation, and this is the tail current what we had it using ISS. The same current ISS will be flowing through this, and this ISS is divided across the two branches, which is ISS by 2, right? And this is your VO1 and VO2, right? So now this is the two important thing what we have to do now, that is we need to give the input DC input which is common for both the input, and ensure that the transistor should be in saturation region, right? So now we will analyze it through here, like V in and transistor M1 and M2 and M3, and what will be the V out, right? So if we have the input which is common mode input, we have V in CM is 0. When the input is 0, what happens? Both the transistor M1 and M2 will be off. Both the transistor M1 and M2 will be off, whereas the transistor M3, so here the biasing voltage will be given so that the transistor M3 should be acting as a constant current source. So this biasing is given to the gate terminal, but the drain terminal will be 0. So hence the drain terminal of the M3 is 0, the gate is at higher potential. So with the relationship between the VDS and VGS, this transistor M3 will be in deep triode region, right? It will be in deep triode region, and the output will be equal to VDD. The output is maximum because the input is 0, right? So now when you apply a small positive voltage greater than threshold voltage, for example, so if VICM is greater than threshold voltage, what happens? M1 and M2 starts conducting, right? M1 and M2 starts conducting. Since M1 and M2 starts conducting, the drain terminal of the M3 will possess certain voltage, right? The process certain voltage, and because of small amount of current will be flowing through the branch, each branch through the transistor M1 and M2. So this drain terminal of M3 will be possessing a small voltage, right? And we can consider that it is not greater than VB, and hence we can say that M3 is in triode. From deep triode it is in triode region, right? And output, what happens? So since your output is VDD minus ID RD, now in this case ID is not 0 because your input is small positive voltage which is greater than threshold voltage. So the output voltage starts decreasing from VDD. Okay, the output voltage starts decreasing from VDD, right? So now I have to increase the input, common mode input, such that the transistor M1 and M2 should be in saturation region. How should I give that input? So we ensure the transistor in saturation region by knowing the relationship between the VDS and VGS, that transistor should be in the saturation region. So now what I do, I will give the input voltage which is equal to the VDS of M1 should be greater than VGS of M1, right? VDS should be greater than VGS. right? VGS plus VGS minus VT. So what we do, we in CM, I give it as VGS1 plus VDS of M3. Okay, so I will give the input voltage as VGS1 plus VDS of M3. So with this sufficient voltage, there will be a sufficient current flowing through the transistor M1, and the drain terminal of M1 is large, so that the M1 and M2 can be ensured that it is in saturation region. Okay, so M1 and M2 can be ensured that, since it is common for both M1 and M2, we can ensure that it is in saturation region, right? And since we have increased the input common mode, the drain terminal of the M3 is anyhow large. Since M3, the drain terminal of any is larger compared to VB, we can ensure that it is in more saturation region. The transistor M3 is also in saturation region, right? And what will be your output? Output will be VDD minus ISS by 2 into RD, right? This is the output what we get here when the input is VGS1 plus VDS M3. This, you see here, this is the minimum voltage what we are ensuring, right? So this is the minimum voltage what we are ensuring the transistor to be in saturation region. Okay, so if I increase it further, so it will also have the maximum limit for the DC input, right? So if I increase this the input common mode, up till what value I can increase? Up till what value I can increase the input common mode? So we know that for any transistor, say for example this is a transistor, we ensure that the transistor is in saturation region if both the drain and gate terminals are shorted, or both the gate and drain terminals are at same potential, right? So here, even if you keep on increasing the gate terminal, you can increase the gate terminal compared to your drain terminal by how much? By a small threshold voltage. You can increase this input voltage, the gate voltage, by a factor of threshold voltage. That's it. You cannot go it beyond that. Even though if you increase it beyond that, it remains the same. The current remains same. So what happens? The input common mode, okay, VICM, input common mode maximum value what you can give is, so whatever the drain value you have plus the threshold voltage of this, right? So now what is the drain value of this the drain value of this transistor M1 you have? It is VDD minus ISS by 2 into RD plus VT. This is the maximum value you can give so that the transistor M1 to be in the saturation region. So with this what happens? Your both M1 and M2 both will be in saturation region, and since the VICM is increased, the drain terminal of the M3 is still more increased, and this M3 will be in still more saturation region, right? And the output will be same, VDD minus ISS by 2 into RD. This is the maximum output voltage what you will achieve. So here in this case what happens? This is the maximum current what we are giving. Maximum current what we are giving. So the input common mode, right? So what you say? The input common mode, the range what you can give is, the minimum is VGS1 plus VDS sat of M3 to what? Maximum is VDD minus ISS by 2 into RD plus VT. Okay, so this is the range in between what your between this VGS plus 1 plus VDS M3 to maximum value is VDD minus ISS by 2 into RD plus VT. This is the maximum range, right? So this is the input common mode range, right? So this is the maximum and the minimum DC voltage what we give to ensure the transistor M1 and M2 to be in the saturation region, right? So this is the important point to analyze to know about the DC analysis. The DC input, that means the DC biasing what we are giving to ensure the transistor in saturation is the minimum value is VGS1 plus VDS of M3 and the maximum value is VDD minus ISS by 2 into RD plus the threshold voltage of M1, right. So this is the maximum and minimum range, the maximum and minimum DC value what you can give it as an input for the differential amplifier. That means you are biasing it to ensure the transistor M1 and M2 to be in the saturation region, right. So this is about the DC analysis or the common mode operation, right. Now coming to the AC analysis or the small signal analysis, right. So here for the small signal analysis we will again consider the same circuit. So these are both are NMOS transistor RD and this is VDD, right. So this is V in 1 and V in 2, right. So now what we have done so far, we have discussed about V in common mode, what we are giving, that is the DC voltage, right. So now for the small signal analysis what we do, we give a small amplitude of input signal on this DC signal, right. So this will be your V in 1, right, and again the small input on this DC signal V in common mode, which is minus V in, okay, V in 1 and V in 2. This is, since both are mentioned as V in 1 and V in 2, it might be of different value. So this is basically the analysis of the differential signal also you can call it, okay. So this is VO1 and this is VO2, understood. So here what we are giving the differential input V in 1 and V in 2. For the differential input we will consider V in 1 minus V in 2 as VID, right, VID as the differential signal, right. So now the differential signal we are applying it to both the terminal means for M1 and M2, the gate of M1 and M2. So here what is the input that we are giving? So V in 1 can be equal to VID by 2 and V in 2 is minus VID by 2, So this is the differential signal what we are giving it for the input for differential amplifier, right. So note that before that we have already biased the transistor M1 and M2 by giving what, common mode input, right. Common mode input means this V in CM, this is a DC analysis where we have fixed the input DC level and it is not a fixed value. You have a maximum and minimum limit, right, what we have discussed here. So that is the maximum and the minimum limit, you have it here. You call this as input common mode minus, that is minimum, and this to be as input common mode plus the maximum range, right. So these are the two maximum range on which your AC signal is set, AC signal is sitting over here, right, and it is differential signal. So the differential signal means you can give two different signals over here. You can give two different signal like V in 2 and V in 1 likewise, right. Or you can give one input signal which can be differential like this as V in 1 and this as V in 2 to the input of second terminal, anything it might be, right. So that is input common mode. On that we are giving the differential signal which is VID by 2, that is the AC signal over here, right. On the DC signal, on the common mode DC input, we are giving the small signal AC signal on the reference, that is DC reference or the common mode input what we have decided, right. So now you see this can be analyzed into two different ways. So the one thing is we assume that the transistor M1 and M2 are same and RD of both the branches to be same. So assuming this there is a symmetry in this circuit, by assuming the symmetric in the circuit, we can analyze this as a two different analysis. We can make this two different analysis. That means the circuit is symmetric, and the input is asymmetric, okay. The input is asymmetric, that means V in 1 and V in 2 need not be same, right. If it is same, what happens? It is the differential output will be 0, right. So symmetric circuit with asymmetric excitation, that is with different input, right. So this we can analyze it in one of the way. So rearranging the same circuit like this as two different linear amplifiers which are connected like this, with reference to some, right, and here you are giving the input VID by 2 and here also you are giving the input minus VID by 2, right, and these two are basically the amplifiers, okay. So these two are basically the amplifiers. Amplifier means it is a non-linear system. You make it linear by operating it at only small linear range, right. So if you have the properties of this 1, 2, 3 at particular range, means linear range, you are going to operate, right. So now we have a symmetric in this, means we are measuring this output of individual transistor with respect to this center node. Okay, how do we analyze this? So we analyze this by superposition principle, by applying two input, that you have two different inputs. By applying one input at a time, you analyze what is the output and you are going to sum the output at the end, right? So for example, you make the input of the left side system as VID by 2 and the right side system to be 0, right? In this case, when you give the input VID by 2, your output can be Vx, Vy and Vz, say for example. Okay, it is Vx, Vy and Vz. So now for the second time you make the input of the left amplifier to be 0 and input for the second to be VID by 2. If the input for the second right side amplifier is also VID by 2, means what will be the output? Output will be obviously this also Vx, Vy and Vz, right? So if my input is minus VID by 2, if my input is minus VID by 2 means the output will be minus Vx, minus Vy and minus Vz, right? It is minus Vx, minus Vy and minus Vz. So now if I apply the input at the same time, that is I apply the input VID by 2 to the left amplifier and minus VID by 2 to the second amplifier, what happens? What happens? The output will be the output at this node. The output at this symmetric node will be what? Vx plus minus Vx, Vy plus minus Vy, it will be 0, right? So that means the potential at symmetric node is 0, right? So in the same way, if I consider this as my symmetric circuit, the potential at the symmetric node can be considered as 0, right? So if I analyze the same circuit and if I analyze with respect to the first point what I considered the symmetric circuit with asymmetric excitation, the potential at symmetric node will be equal to 0. That means the potential at this point will be equal to 0, right? So the potential at that particular node, the drain terminal of M3, will be equal to 0. So I can analyze the same circuit as by taking one half of the circuit, right? By taking only one half of the circuit, by connecting this to be 0. Okay. So here considering one half of the circuit, that is, which is nothing but this terminal. What terminal? This terminal I have taken it as 0, right? This terminal I have taken it as 0. The potential at the symmetric node here, it will be 0, I have considered. So this is the input what I am giving, which is VID by 2 and this is R and this is VDD, right? So with respect to my input VID by 2, my output will also be V out by 2, right? So output will be V out by 2. What do you mean by output is V out by 2? What is your expression for the output expression for the common source amplifier, this circuit, which is minus gm into r into vid by 2, right? So this 2 and 2 will get cancelled, so your V out by VID will be nothing but what? Minus GM into RD, which is nothing but your voltage gain, right? So even the input is differential for this differential amplifier, by the property of symmetric, by making this symmetric node to be 0, right, the gain remains same, right? So this is half circuit analysis, right? So this is half circuit analysis, differential input, right? So we will take an example, one of the example on the same. So for example, if I have a circuit like this, which is differential amplifier circuit with PMOS load, this is the current ISS. So this is plus an input common node. So this is the input AC signal what I am giving, okay, and say this is diode connected, this MOS is diode connected, this is M1, M2, M3 and M4, right? So now in this, calculate the differential voltage gain for the given circuit. Assume the channel length modulation of the transistor should not be equal to 0, right? So this is one of the example what we consider, right? So what is the question? We have to find out what is the differential gain, right? So the differential gain of the transistor. So considering the half circuit what we have done, so considering the half circuit analysis like we did earlier, and considering the input is anti-symmetric, okay, considering that the input is anti-symmetric, so now what happens? That means at the line of symmetric, the potential is 0. Understood? At the line of symmetric, the potential is 0. That means considering the half circuit of this is PMOS, this is M1 and this is M3, and this is VIN by 2, the differential input, okay, and this is the potential at the symmetric node, which I have taken it as a reference, which is equal to 0. So if the input is V in by 2, output at this node will be again V out by 2, okay. So now this is nothing but a what? The common source amplifier with PMOS as an active load, right? So we know the expression, what is the gain expression or output expression? V out by 2, which is equal to the GM, the total transconductance, and the resistance, if you remember, means if we have already analyzed this, considering the lambda is not equal to 0, since lambda is not equal to 0 for all the transistor, so R naught will be present for all of them. So here M1 is the active device, so GM1 into the R naught 1, the output impedance of M1, parallel with 1 upon Gm3, the transconductance of the transistor 3, parallel with R0 3 into V in by 2. This will be the output, and the gain eventually is nothing but minus Gm into the impedance, total impedance what is seen with respect to that node, which is R01 parallel with 1 upon Gm, the transconductance of M3 parallel with R03, right. So this is the differential output for the circuit. Your AV differential gain, which is V out by V in for this circuit, is minus Gm1 into R01 parallel with 1 upon Gm3 parallel with R03. So if you approximate, the value of R01 and R03 are large compared to 1 upon Gm, so you can approximate it to minus Gm1 by Gm3. So this is the differential gain of the given circuit, right. So by this, what we have analyzed, so the common mode operation, that is the DC analysis. So we can also analyze this with respect to the graph considering the maximum and minimum value. So that is if we consider the differential input V in 1 and V in 1 minus V in 2, considering the differential input, so your VO1 or VO2 will be the DC range. The DC range will be something like this, which will vary from VDD to VDD minus ID RD, ID by 2, right. So this is ISS, that is ID by 2 into RD. This is maximum ID, okay. So this is ID by 2. This is the point which is equal to half of the current, and this is the maximum current, right. So this is VO1 and this is VO2 during one particular point, right. So the output varies from VDD to VDD minus ID RD, and this DC reference is nothing but VDD minus ID by 2 into RD. This is the DC range what you come across in this, right. So here we analyzes that the common mode operation, that is the DC analysis, which ensuring that the DC biasing for the amplifier to ensure the transistor to be in the saturation region. So we have to ensure all the transistor M1, M2 and M3 to be in the saturation region, and M3 is nothing but this current source. We used to design this current source by making use of this transistor M3 giving an external bias VB, right. And we have started increasing the input V in common mode, which is common for both the terminal. So from 0, M1 and M2 is off, and M3 will be deep triode region, output is maximum. And if you start increasing the input, DC input, the M1 and M2 starts conducting, and M3 will be in triode region still, and the output voltage starts decreasing from VDD, right. And the input minimum what you can give to ensure the transistor M1 and M2 to be in saturation region. This is the minimum input what you can give, okay, for the transistor M1 or V in CM, which is common for both M1 and M2 in fact, okay, VGS plus VDS of M3. This ensures that both M1 and M2 in saturation region and M3 will be in saturation region, and output is VDD minus ISS by 2 into RD. And the maximum value what you can give is VDD minus, that is the maximum what you can give here for the gate voltage is threshold voltage greater than this VDS, okay. So the VD voltage is VDD minus ISS by 2 into RD plus VT. This is the maximum value what you can give, and to ensure that M1 and M2 in saturation region and M3 will also be in saturation region, and ID means output still decreases, but which is almost equal to VDD minus ISS by 2 into RD, because it is a common mode and it is the same input going for M1 and M2, and obviously it will be the same current which will be flowing through both the branches or both the transistor. Okay, so in this we come across the input common mode range, the IMCR, which is, this is the IMCR minimum and this is the IMCR maximum, to ensure the transistor to be in the to give the DC biasing to ensure transistor in the saturation region. So now coming to the differential analysis, differential signal or the small signal analysis. So what we do here, we give input V in small AC signal on the common mode input or the DC input, what we have discussed earlier, within which is set within this range, in between this, right. So this is the small signal what we are giving for the input 1 and input 2, and since it is a differential signal, we are giving the input 1 and input 2, if the magnitude are same, the phase will be different, right. So the phase of V in 1 will be 0 and the phase of V in 2 will be 180 degree, like, right. So the differential input can be given by two different sources, to input 1 and input 2, or by giving the same sources, by giving positive potential to V in 1 and negative potential of the source to V in 2. This employs the differential input for both the signal. So here for the analysis we have considered V in 1 minus V in 2 to be a differential input VID. Okay. So the signal what we are giving here for the V in 1 is VID by 2, half of it, and V in 2 is minus VID by 2, right. So in this we have two types of analysis. One is symmetric circuit with symmetric excitation. With symmetric excitation, what happens, the output is anyhow 0, and the another one is symmetric circuit with asymmetric excitation, that means different input, differential input. Okay. So this if what do you mean by symmetric or the symmetric, here you can analyze by having two different amplifiers, what I have mentioned here. If they are connected, then the differential output can be analyzed by individual, considering one at a time. That means superposition theorem. Okay. So for example, first we give an input for the left amplifier, input VID by 2, and output for the means input for the second right amplifier is 0 for the first time, and during that the output for the left amplifier is Vx, Vy and Vz, and similarly for the other side, if I keep left side input to be 0 and the right side is VID by 2, it is same Vx, Vy, Vz. If it is minus VID by 2, it is minus Vx, Vy and minus Vz. So if I give both the inputs, then the potential at this symmetric node, okay, I am not taking the potential at this at node here to here or here individual. What I am taking the potential at symmetric node, at this particular node which I have considered for superposition theorem, happens to be Vx plus minus Vx, which happens to be 0, right. So this is the symmetric circuit what we have analyzed, right. So here considering this potential at the symmetric node to be 0, which means this is the symmetric in the circuit. We have assumed all the transistor M1 and M2 is same, RD and RD are same, whereas M2 is different, and this is the node in between these two branches or these two amplifiers. So considering the potential at this node to be 0, we analyze it as a half circuit analysis, which we can analyze it like in common source amplifier. For the input VID by 2, you have V0 by 2, which is equal to minus GM into R times of VID by 2. So here still the differential gain remains same, it is still minus GM into RD, the drain resistance. right? And again we have solved the same examples considering the same circuit.